I think that simulator has this like huge scaling promise. You take any scenario you saw, and you release the agents, and you release yourself, and you can try all kinds of stuff, and they can try all kinds of stuff.
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lucas Biewald. Today I'm talking with an old friend, Drago Angelov, who is currently Distinguished Scientist and Head of Research at Waymo. He's been working on image models for at least the past 20 years and was another student of Daphne Koller, who is also on this podcast. This is a super fun conversation. I hope you enjoy it as much as I did. My first question is something I hadn't realized, which is that you're one of the authors of the original Inception architecture,
That's
which
right.
I
Yeah.
should know, but I somehow missed that. But can you tell me how that came about and what you were thinking about at the time?
So actually, the story goes back even before. At Google, I worked on Street View for a bit, which was related to autonomous driving, and one of the areas where actually computer vision used to work pretty well. There were two: face detection, license plate blurring. That worked pretty well at the time. And the other thing that worked really well is 3D reconstruction from cameras, from LiDAR. So that's what I used to work on, bundle adjustment and so on.
And were those deep learning models at the time?
None of them were deep learning. Actually, we had one person in 2008 or 9. He came from Microsoft. I think his name was Ahmed or Abdul. And he used deep nets to essentially detect and blur license plates. And everyone was very unhappy that he used deep nets. And because it was his own code base and no one else was doing anything like it. And of course, you could modernize and upgrade it by doing support vector machines.
Right.
So eventually people, tried to modernize and upgrade with support vector machines, the neural net things, and they didn't quite succeed. I think they regressed a bit, but everyone used technology they understood. So I think I didn't work exactly on that problem, but I think it was at the time that's how we used to do it. So that was in 2009, maybe in 10, right? And after working in this field, I decided that maybe I should do something more adventurous in my career and join a team in Los Angeles that essentially was called Google Goggles. It was not the glass. It was a little app that did computer vision, and we used to use it for experimental computer vision tasks. And so there we started experimenting with different applications, of learning and deep learning to computer vision. How do we recognize these objects in these pictures? And at the time, there was a time when, I was a tech lead manager of a small team. There were 4 of us. And half of us did, graphical models, deformable parts models. And, you may be familiar, when I was a student of Daphne Koller, we did a lot of those. And then half of us, like the other half, we were experimenting with deep learning. And that was Christian Szegedy and Dumitru Erhan. And so in those early days, the deep learning models at Google were something that was called QuackNet, which is a non-convolutional big neural network that Quark, a student of Andrew Ng, brought. And for a while, we were trouncing it with deformable parts models. And I was working with an intern who later became a Googler. We had the best deformable parts type detector, even collaborated with Professor Deva Ramanan. He was also in the LA area at the time. And so we had a collaboration, built something nice. And so that's where Christian Szegedy came in. He was actually on my team, right? And for a while, the deformable parts were beating the deep nets. But then eventually AlexNet came in, and then all of a sudden, no custom solution could beat the deep nets. And so switched to this, but we were early on this already. We had people that had been doing this for a while. And so 2 interesting things happened. We started optimizing the architectures, because partly, actually in Google, that was the easiest thing to do, because the system for training them, it was called Disbelief, was pretty unwieldy. And so you couldn't be too smart. So the easiest thing to do is to just tweak the architecture. Mm-hmm. And so we're tweaking it, and Christian one day comes to me and says, "Hey, Drago, I have this idea, it's a Hebbian-inspired idea. I'm going to train this new architecture." I was like, "Oh, Christian, very nice." I mean, we had been playing too. I had some versions of architecture that was 1 or 2% better, something. Christian is, what part do you change? It's like, I'm going to change everything. I was like, oh, that's a great engineering approach. Like, why, aren't you worried that, who knows what will happen? No, I have a good intuition. I'm already training some. It's doing great. Like a bit later, he's like, look at this thing. It's like, it beats anything we've ever seen. And that's when we decided to do also the ImageNet challenge. We had this and some detector work as well. SSD came out of it. That's also a very strong contribution by Christian. So, but he was bold and he decided to just try more ambitious things. And in these early competitions, people still tried to do a lot of smart things in the old style. They tried to embed known algorithms in the networks instead of making the networks better. And we, for good or bad, were in the environment where it was the easiest thing we could do is make the networks better. And so that's what we did. And I think that really helped early on.
What was the intuition that he had to, what was like the tweak that really made a difference?
I mean, I think there is, if you remember the Inception architecture, it had this, in each module, there were several paths. And so one path was do one by one convolution. So mostly just adding depth processing. Then it was 3 by 3 and 5 by 5 convolutions. And those were adding, like expanding the receptive fields, right? And then you had a separate channel for each, which kept the model still tractable. So it's not like number of inputs times number of outputs. So you had some, maybe it's something like block diagonal, not quite structure, because now you had 3 channels, and then you again condense the information from those. That was the idea of this idea for a block. And so it's a nice compact way to still add a lot of rich structure and depth. And so that was, I think, very powerful. I think if you ask Christian, he'll give you a whole other story why he came up with this model. I'm not sure I'm the best person to channel it. You should invite him. I mean, he did a lot of these early visionary things, so, but we all worked on it together. Yeah, and that's how I was part of it. And the other thing again, Christian was very involved. We discovered, this was 2013 or so. So deep nets we used a lot for classification, but not many had used them for detection. And so Hartmut Neven, who was our director, came and said, hey, Christian, like, I have this idea. I think some of it comes from Christian. Like, let's make a better detector. We just, backpropagate the signal through the network and see which parts of the image caused it to fire that it's a cat. And then if you do this, you will find where the cat was, because the network will highlight you the cat. And so we're like, oh, that's a cool way to do object detector. We can mostly use a classifier. Let's try it. And so we tried a few versions, but Christian tried it, and it's like, it doesn't work. And it's like, why doesn't it work? Well, the image doesn't change. Now it says me it's not a cat. It's whatever, giraffe. I mean, you name it.
Right.
And we're like, that's strange, right? And like, he debugged for a long time. I mean, it's also like, at the time the system was complicatedly written. It was not easy to debug. Maybe 2 months he debugged, including trying on MNIST. On MNIST, you could do the same. And then eventually we realized, okay, something's happening here. There's these adversarial examples. You can just flip the label without much visible any changes in the image. But we set off to discover a detector. And then ultimately he ended up with the paper. They bunched several discoveries in that paper, but by far the primary one was the adversarial examples.
That must have been an exciting moment. Did it feel like these image tasks were getting better much faster at that time, or did it feel like a gradual change?
I mean, it was a very exciting time, right? When a new set of whole new field opens in front of you. Let's try to do computer vision with deep nets, and most of it hasn't been done. And most people are not doing it either, right? I mean, there were a lot of developments at that time. Like every few months, something pretty major happened. I mean, strangely enough, this continues. If you caught a bunch of people in 2015, 16 and say, okay, what's left in computer vision, in 2D computer vision, how much should we do? No, we're pretty good already, I mean, that's why I went to self-driving. I was like, okay, 2D computer vision on images is pretty good now, like in 2015. Let's do cars. That's a whole other game. Like, but now, early on, there were a lot of big developments, like batch normalization came out. Sergei Ioffe and, again, Christian Szegedy were involved. That's down the line. I mean, in Google Brain, people did a lot of really cool things. So it was just like, one after the other, there was a group of people. That was also a time when a lot of academics came to Google to do deep learning. Right. Later, a lot of them went back to academia. They realized they can still do it there. For a while, it's like we just need to do it in the big companies. There was a bit of this. At least that was my exposure to it. Maybe people have different interpretations. It kind of went back and forth. Now with the what people call foundation models and the big transformer language models, people say maybe we should be in the industry again, right? But there was a time when people could go back to academia and not feel too deprived.
I think there have been 4 versions of Inception, right? Are people still working on improving these architectures, or does it feel like we've kind of squeezed out all the improvements from that?
I mean, it's moved on. There's actually a guy on the Waymo research team called Ming-Hsin Tan who worked with QuoCLE, the famous QuoCNet I described. That was not convolutional. Of course, not hey Quark, I don't mean anything bad. These folks doing great work. I think Christian just moved away from trying to improve the architecture. So there were Inception, and then I think Francois Cholet, who also was briefly on the team I led at Google, that was still 15, who did Keras. He had, I think, Exception or Nexception, another
Yeah,
variant.
that's in the
He's
Keras library.
simplified.
Yeah, for sure.
Right. So he developed that. I think afterwards, now people move to the large transformer models, right? So XCIT and Swin transformers, I think, and Google. So Ming-Hsin Tan's own work. There's a model called CodeNet. So in our times, we top one on ImageNet, we would get maybe 70% accuracy, and of course, top 5, it's a lot better. People used to score at top 5. Now people can get, I think, 90% top 1 with a lot of pre-training on large data set and other things. But this CodeNet is a hybrid CodeNet transformer, and it's dramatically bigger than the models we used to train, and it's pre-trained on a lot more stuff, potentially. But people have pushed what's possible in ImageNet a lot further. Now, I'm not sure how much yet further you can push it, given the inherent limitation of the data set.
Right.
But I mean, people are very good at ImageNet with different technology than what we used to do.
And what's the inter-annotator agreement on ImageNet? How will the humans do ImageNet?
I have no idea. I mean, in the old days, Andrei Karpathy, he did a test where he tried to label the test set after training himself. And I think the models were competitive with him. So by now, I think they blow humans out of the water. Speaking of Andrei Karpathy, actually, it's a small world, but in 2012, when we were doing deformable models and deep nets, both, actually was going there with the story, and then we went to other directions. I had the chance to pick either Andrei as an intern to do deep learning, or a guy called Qianxin Zhu from Deva Ramanan's lab to do deformable models. And I picked Qianxin Zhu, right? So never get to work with Andrei, maybe to my peril, but yes.
Well, I remember I interviewed with you to be like your like little research assistant as a master's student, and you chose Jimmy Peng, who is a very, very talented guy.
He's a very talented guy. I'm sorry. Don't hold this against me.
It's a good choice. I can't hold that one against you.
Hopefully worked out for all of us.
It worked out for everyone, yeah. So, I mean, I'm really curious about, you've been in autonomous vehicles for quite a while, and I guess from the outside, it sort of feels like autonomous vehicles are kind of steadily improving. Sort of feels inevitable to me, I guess, but so hard to tell, like when, really, be able to just like kind of purchase an autonomous vehicle and ride it. I'm kind of curious, like I'm really curious about what your thoughts are, where things go, but have there been like major breakthroughs in autonomous vehicles in the last like 10 years that you've been working on them, or has it been really like an iterative process?
So it's an interesting domain because, I wasn't at Waymo early on, but people that were at Waymo were very proud of the demos they can do even 10 years ago, 12 years ago, right? Waymo is 13 years old. I mean, we've worked on the problem a long time. As everyone also understands, it's the very rare cases that interactive rare cases that you need to be robust, and all the possible failures that you need to be robust, that makes it so hard. A lot of these improvements are not so easily perceptible. So in the early times when you sit on a vehicle, I mean, feels pretty good, you know. But you need sometimes dramatic improvements under the hood to make sure that it's really pretty good and comparable to humans. I mean, humans ultimately are pretty good at driving, all things considered, especially when they pay attention, right? Which of course, that's one big advantage of autonomous vehicles. They always pay attention. I would say that over the last 10 years, and I'm happy to be part of the process. That's why, like just in computer vision, but here even more obviously, I think the entire technology is being rethought ground up. I think machine learning takes constantly more prominent roles, and the types of machine learning and the models we do continue improving at a fast pace. And so there is a lot of capabilities, and I think you can see that for a while maybe there were no notable launches, right? Even though you would hear about the space. Now people start launching things, right? I mean, Waymo launched the first fully driverless service in Phoenix in 2020, right? And in public, I think we've driven over 500,000 miles in autonomous mode, right? And in San Francisco, we started driverless operations. That's another big milestone. I mean, we're building a stack that can handle, car, truck, highway domain, cities, but it's one driver still. But these are deployments we're having. We announced we will launch downtown Phoenix. I was on the car actually in San Francisco in a driverless operation maybe 10 days ago. It's awesome, right? And I think when you start seeing milestone like this, right, they're meaningful. Now the truly meaningful milestones is when you release it at large scope and scale, right? It's just you want to do it in a thoughtful manner, make sure that you're confident when you put these things out there that they interact well with people and are safe for everybody.
When you say sort of that the autonomous vehicles have been really like redesigned and machine learning takes a more prominent role, could you give me a flavor of what the trends are? Like, are things moving to a more kind of end-to-end system where you just like, the inputs are like a camera and the output is like which way to turn the steering wheel? Or are things becoming more componentized where like each piece is responsible for something? Like, what are the big trends over the last 10 years?
So the main trend, I would say, and I've tried as a lead of the research team at Waymo, which does pretty much primarily ML almost exclusively, right? But we started maybe applying to perception and then prediction and understanding behavior and then planning and then in the simulation, right? I think it's permeated every aspect of the system, on board, off board. There's machine learning in all these components. I mean, not major models, meaning they're not just small features, they're core parts of the system. And I think that's on the macro level, that's a change that's definitely happened at Waymo. I think when people started, right, early on in 2009, there was the famous Sebastian Tran book. It's like probabilistic robotics, right? There you have the LiDAR. You can create all these segments out of the LiDAR. Then you can reason about the segments. You can build, like initially people, without the deep learning models, you build a very modular stack with very many modules. Each does a little something. You put them all together. It's a significant engineering challenge. And the trend has been larger and larger neural nets, right? Doing more and more, potentially going from neural nets in narrow scope to neural nets in wider scopes. Maybe neural nets from one task to neural nets to do multiple tasks. So the trend is for the modules, with the help of machine learning models, to grow larger, right, and fewer. Now, there is an interesting question, and this is an area of exciting research, and not only, I think, in the industry, some companies, espouse a fully end-to-end learned approach. And there is no clarity yet if fully end-to-end learned system is actually better. There is in life, I think, when you build these things, there is often trade-offs between different extremes, right? So each of these things has its pluses and its minuses, and you want somehow to take advantage of the pluses, but not to be stung too much by the minuses. And so we were maybe too much on the end of too modular system, too many small pieces written by engineers. Whether the answer is several or large modules or a single end-to-end thing, I think is an open question. I think this is an area that we're still, as a research team, we're exploring the repercussions of these things. But the industry is exploring because people have different vision for some of these things, right? But I would not say there's some serious trade-offs to doing everything end to end. Not in academia, by the way. If you take an academic data set and you train more end to end in the small scope, you will probably do better. But that does not mean you built a better system in the production setting.
Why is that? What are the pitfalls?
I think ultimately, academic setting, you look for a lot more like average metrics on things, right? And the data set is small. So clearly, if you build something that incorporates everything and co-trains, you will probably do better, especially if you optimize on it. In the production setting, you're looking to be robust to the very rare cases. You look at speed of iteration and ability for people to fix your model if there's issues, right? You look at testability, like understanding there is issues, being able to dig in. Simulation requirements too, right? So if you have fully end-to-end model, now your simulation has to be end-to-end, and you need to simulate all the sensors as needed and so on. Right? That's maybe a lot more expensive than some intermediate representation that may be simpler to simulate, maybe does not pass all the information the model may want to pass, but at the same time, you get other benefits. Maybe you can train closed loop, right? A lot faster. That now also can help you. And so there's very interesting trade-offs in this space.
I think one thing that I've really noticed from, my vantage point of selling tooling to autonomous vehicles is how many customers there are for for labeled data and then, weights and biases stuff. Like, do you think it's a kind of a wasted effort that so many different smart teams are tackling the same problem? Do you feel like there's a diversity of approaches that's interesting? Does Waymo have a specific point of view that's like different than Zoox or other places that you know of?
I think if you start looking at the stack, first of all, you don't really know. I don't know exactly what the stacks of the other companies, right? They're proprietary. I think there is an interesting, search space where you're saying, I'm going to design this system. It will have these APIs. These are the intermediate outputs. This is how I build my tooling. This is how I understand how the system is doing. This is how I iterate on each of them. That's why this representation is beneficial, say, for onboard perception, onboard performance, or for example, in simulation, right? You take all this into consideration, it's a very wide search space. I think every company ends up with somewhat different APIs, design choices, trade-offs on how modular versus not, trade-offs on how much machine learning they put versus not, right? This is very understudied because ultimately it's hard. I think in research, it's a lot easier to study every one problem in isolation, and you can say, okay, let's do 3D flow prediction, right? Like we have some state-of-the-art 3D flow prediction or monocular depth, others do. I think when you start combining them, there's actually a lot of variability possible, and people's stacks end up quite different in the end. Even if on a high level, you can say they're somewhat in a similar vein.
Interesting. I guess, do you feel like there's still kind of deep problems to solve between now and everyone riding in autonomous vehicles?
Scalability is always a problem, right? So safely, cheaply scaling to, say, I always think, what system do I need to build to scale to a dozen cities cheaply?
Uh-huh. But wait, I want to understand that because, with a normal piece of software, you wouldn't only deploy it in San Francisco and Phoenix. Like, it would just, if it's safe in one city, it'd be safe in every location. So what makes it hard to, like, I don't know, go to LA and have the same thing deployed, or go to Boston and deploy it? Why does it have to be one city at a time versus, like, usually software kind of goes everywhere at once?
So I think we're at the point where we're building software that should deploy most places and be pretty good at it, right? Maybe historically with the probabilistic robotic stuff, that wasn't quite the case, right? Still, you need to validate that and be sure, right? And I think there is a lot of local particularities in every location that you should make sure you can handle. Like there's some strange roundabout in this place, and there is some 8-way intersection in this other place, and maybe here in Pittsburgh they do the Pittsburgh left that you need to understand, right? So someone needs to go still, collect data from these places, potentially tune the models on these places, potentially then do the safety analysis to convince yourself you actually should deploy, right? And that is work. That's why you don't just build it once and, okay, let's just drive and see what happens. I mean, you can do that, but if you actually remove the driver, I'm not sure how responsible that it is. All right.
But I mean, Google has actually mapped like every city on the planet. It feels like, shouldn't it be possible to send some cars and collect data?
I mean, we are sending cars and collecting data, right? So we're growing our scope. So now we have like Chandler in Phoenix, now San Francisco we announced. Now, downtown Phoenix we announced that we will deploy starting this year. We're collecting data if there's been, public postings in New York, say in the winter, and in Los Angeles. And of course, we now have trucks collecting highway data for trucks and behavior around trucks, which is important, I think, right? There's somewhat different behaviors around trucks and different issues like, seeing around the trailer, for example, that you don't have with the car, and you have somewhat different sensor configuration. So we're broadening, right? I think the core is, and I agree with you, if you look at every city as one deployment and one piece of software, and you just develop it and launch it in that city, I mean, that doesn't scale, right? So the way we think of it, we're building one driver, if possible. This driver is able to handle all these environments as possible, including potentially as much as possible cars and trucks, even though there will be some small differences, but the core of all pieces is similar, right, in the nature of what they want to do. And then you iterate, and when you're comfortable that you have enough data about safety and passing the bar, you launch.
Do you have an opinion on LiDAR versus vision-only approaches?
By the way, maybe one more topic on the previous question. I think if you ask what are the big open questions, right? I think one of the interesting topics is, and this is a scaling factor for you, you want more machine learning in the planner, if possible, and you want a realistic simulation environment where you can just replay full system, scenarios, and without too much human involvement determine whether you're improving or not improving. So for us, the big challenge is it's a very complex endeavor, because essentially it's not like someone gave you the perfect simulator for autonomous vehicles. So you need to build one, and ideally you build one from the sensor data and the data you collected. So that's like real to sim.
Right.
And now, well, by what metrics do you build the simulator? You need to establish metrics for the simulator that constitute acceptable simulation. And for us, simulation, a lot of it is about behavior of agents. It's not just how something looks, even though we like do that work too. We've done NERF and 3D reconstruction and all kinds of things. But ultimately, the behaviors is some of the main things you need to solve. So you need realistic behavior in the simulator. And then when you have that, then you have the other metrics, which says what does it mean to drive well in the simulator in the world, right? So you need both. You need to build both things. And the further you go, the easier it is to improve these pieces, because the less you need humans in the loop, right? We can still improve them. You don't need perfect realistic simulator to improve your driving. It's just it requires more human judgment, right? And but there is a process to I mean, in these areas, a lot is possible still, right? And we hopefully will show more interesting work. This year, we sent a couple of papers in the space that people may find interesting.
Cool. And that might even be applicable to things outside of autonomous vehicles, right? It seems like sim to real type stuff is necessary for any kind of robotics application.
Yeah, or real to sim in some sense. I mean, the specific instantiation is maybe a little different, but I would say that that's one of the nice properties of AVs is that it is a complete robotics problem. Maybe it's of a specific kind, but a lot of the things you need to solve for other robotics problems are at least in some shape covered. And so there will be hopefully a lot of positive spillover from our domain to others.
Okay, well, a couple practical questions that everyone on the team wanted me to ask you, if you could talk about it. I guess, do you think that the do you have an opinion on sort of LiDAR and more complicated sensors versus vision only approaches? Like, do you think LiDAR will always be needed to make things safe?
I think ultimately it's a question of, I mean, I don't know if LiDAR will always be needed, but I think it's really great. And I know it's not very expensive, right?
Right.
And I think it even makes your computer vision much better, and it makes your simulation much better, which then immediately also results in better driving. I mean, it's a fantastic sensor that you can just have for now. So why not have it? Right? I think there is this convergence happening in some sense. Like LiDAR is becoming more like cameras. It's higher and higher res, maybe even can do the passive lighting. So then it is a camera also while being a LiDAR. And it's cheaper and cheaper with the current technologies. On the other hand, obviously our 3D perception cameras, even compared to 2 years ago, is dramatically better. Right? I really like having the LiDAR. To me, it's a safety feature. It's a lot safer being in a car with LiDAR than not. Maybe it's theoretically possible to just do it with cameras and maybe it will play out. But do you want to risk it and why? I mean, it's easy to remove LiDAR. No one's stopping you, right?
Sure.
It's not like we don't have state-of-the-art camera approaches. It's easy to remove maps too, right?
Yeah, that's my next question. Yeah, I mean, how critical do you think the mapping is? Because that doesn't seem scalable necessarily, right?
It's pretty scalable. I mean, you can do mapping with machine learning. In some sense, if you design it properly. Generally, maps are a prior. They tell you about an environment, especially environment you drove a lot in, what to expect, what is behind this occlusion, right? What did you, when you looked at this intersection, what does this thing really tell you to do versus not, or what to expect around that corner? If you can have some of this information, why not use it, right? I mean, it's safer.
Right.
Now, should you trust the map as is and require it is correct, right? That's not scalable. If you say the map is given to me, I need to maintain it true, otherwise I can't drive. I mean, you cannot deploy autonomous driving at scale then, right? You don't have a business. I mean, people do construction, put cones, they change the traffic lights, they repaint things on the highways where the trucks drive, they reroute lanes. I mean, you need to deal with this, otherwise I mean, you don't have a business ultimately in the end, right? So you can't like trust maps blindly. But then why not have a prior? I mean, we drive a city and, even to do the safety case or just to collect data to understand what people do. And why not have a map prior?
Right. I mean, do you think it helps enough that there sort of will be one winner in autonomous vehicles that, everyone uses, then it gets better because it collects the map data? Is it that much of an advantage?
Which the map data? I think generally there are scaling benefits in autonomous driving. And I think a lot of these scaling benefits, they accrue when you use large machine learning models, right? I mean, you see the extreme case with GPT-3 and the big language model. Like in our days, when we studied with Daphne Koller, we learned that there is a bias variance trade-off, and you want the Occam razor, you want to penalize models that have high expressivity, and you will get the best generalization, right? So the simplest model that explains your data is great, right? Probably better than some fancy overfitting model. Now all of this is on its head. You say, I want to train the huge model that's much, much bigger than anything on tons of data that may be the same as mine or different, right? And that model will generalize better for me, right?
Right.
Now in AVs, what does this mean? Well, we have all this data. Waymo has, more data than vast majority of companies of different platforms. I mean, we're 13 years driven, 20 million miles in autonomous mode, right? We have 20 billion miles in simulation. Simulation is also data. Now, we have cars and trucks. All of these things, if you take the large machine learning point of view, makes your models better because you have more data. It's more diverse data. It captures, well, we try to see everything that you could see. If you do your job well, these models will actually generalize better. Like it helps you having cars to do well on trucks. And now you have all this great car data, right? Like you add it to the models for the truck, and it helps a lot. And car data is a lot cheaper to collect than truck too, and maybe a lot more diverse. I mean, often on the highways, being a truck, you drive fairly conservatively, right? And fairly few things happen on the highway, but it's a multiplier for you, the multi-platform setting, right? So our domain is friendly to this, I think.
Right. I mean, it seems that, I guess, could you talk a little bit about why Waymo is investing in trucks? It seems to me like a different enough domain, like more different than a different city, that I could imagine. My first thought would be, well, you'd probably get the cities working first with a car and then switch to a truck. But it must not be. Could you talk about that?
So I think there's some difference between the two, but ultimately most of the pieces are similar enough that you can share. You can share roughly the same modular design. You can share roughly similar types of models. You can share roughly the same types of simulation environments. You can benefit by cross-pollinating the data between the two domains. For example, to understand how others behave, right? Like, I mean, you can just collect data of how people behave with cars. It will generalize to trucks, right? There's some unique problems with trucks that do have to be solved. One of them is, well, you need to see a lot further for a truck, partly because a fully loaded truck takes a while to stop. Also, if you want to change lanes for a truck, sometimes you need to create gaps, right? And it takes longer to create gaps and do it without cutting people off unnecessarily than for a car. And so you need to anticipate a lot sooner that now, maybe, and you need to see around the trailer or be smarter how you infer what's behind your trailer. So there are a few of these problems. And, that's why you have a bit different sensor configuration. But if you look at the core pieces, a lot of the other logic, like which modules you would put together, what to put in each module, is very similar. All the infrastructure is similar. Now, trucking is a very big use case, right? It's a big market. And so it makes sense from that standpoint. There is enough cross-pollination and commonality, more so than differences, I would say.
Okay, another question I wanted to ask, maybe you get this all the time, but such a common adversarial example is like, slightly modifying, street signs to make a system think it's a different sign. Is that like a toy thing that doesn't really come up and doesn't really kind of cross your mind as a major problem? Or is that like something that you actually really worry about trying to create autonomous vehicles?
So in our case, we have 3 different sensors, right? And I don't think you can fool 3 different sensors nearly as easily independently. Well, furthermore, we have redundancy between the sensors, right? When you want, part of the beauty of having active sensors is, I mean, one of them can fail and they can still fairly independently detect things for you, right? And so from that standpoint, hybrid stack with multiple different sensors is more robust. That's one. Second, I think generally these adversarial problems fall in the bucket of robustness and, in some sense, unsupervised domain adaptation. You want to generalize to similar situations. And in research, we have studied these topics. We have methods currently that we've investigated that help against either transferring from one domain to another. There is a paper called SPG that we put up. That's an interesting take on essentially adding more structure to your prediction task, detection task, to make you more robust to new conditions. Like you train, say, in sunny weather, then you want to work in rainy weather. Turns out that instead of just regressing 3D boxes, if you first have an intermediate task that regularizes, predicts your point clouds, and fills it in, and then from this canonicalized, regularized point cloud, now you predict your box. Turns out you get a lot of robustness. And we did it with unsupervised domain adaptation in mind. And by the way, in the Waymo Open Data Set, we released some data for people to study this. We can talk maybe more about this later, about the Open Data Set. But so we did it with this in mind. And then we realized, this This method is actually number one on the Kitty leaderboard. Kitty is one of the for hard detection cases in its time. That was maybe a year ago. And that's because when you do well, now Kitty is a small data set. There's rare examples. When you add robustness to domain adaptation and you do it well, it just happens to do well on these examples, on more of these hard examples. And so these are techniques that we are exploring, and we have at this point significant experience with, right? Both the adversarial techniques. There's actually a large space of them. There is a challenge, like many techniques make you more robust to adversarial cases, but really hurt your performance in nominal cases. And the challenge is to find robustness methods to train your models such that you don't regress the common cases. If anything, you get better and you get more robust to the adversarial attacks. And there are such methods.
Well, that's a good segue into something I want to ask you about, which is the open data sets that you've been releasing. I mean, could you maybe first of all talk about, what they are, but I'd love to hear kind of the motivation and, what's been surprising in the reaction from the community after putting them out.
So I would say that when I joined Waymo in 2018, right, and we started the research team, which is applied research team internally, most of our work actually is primarily focused at improving Waymo systems with machine learning, and we do publish too, right, a good amount, but not all our work you see, right? We're not just made for academia. So we wanted to engage better the community. And then the question is, well, how do I collaborate with you, or how do we encourage you to work on certain problems? And at the time, especially when we started planning the data set, there was the Kitty data set, which by modern measures, it was done, I think, in 2010, 2012, was tiny. And so then we thought, okay, well, the best way to encourage people to solve problems relevant to our setup, which is a lot more data, and the problems we're interested in, let's start releasing data, right, that people can just push the state of the art with, right? That's what the community does not have. And so we released what I believe is still one of the largest and richest data sets, and we're actively making it better and better and better. And if you checked it out 2 years ago, even come back and see the kind of things we have now, and we will continue releasing interesting data. So we have 3D bounding boxes over time, 2D bounding boxes over time. Now we have 3D semantic segmentation. We have 2D and 3D post key points for people in busy scenes, type of data that has very little as other data sets you can see in the wild of such data. We have a bunch of interesting challenges. So one of the interesting things is, so we released the perception data set and we picked 2,000 run sequences, which in its time was quite a lot, right? So 2,000 20-second sequences compared to anything else, it's a humongous amount of data. And then we started trying to do behavior prediction task with it. And, if you do this, you realize that for behavior prediction, you need an order of magnitude yet more data. Why? Because, say, a scene of 20 seconds, each has 200 objects, and you may be at 10 hertz in our data set, right? Like that's tens of thousands of instances that you observed over these 20 seconds. And maybe you will see one interesting interaction or not, right, in the whole sequence. And so from this standpoint, then we're like, okay, well, what is a reasonable size of data for behavior understanding and understanding interesting interactions? And we came up, okay, well, if we had 2,000 perception sequences, you want 100,000 behavior sequences. And then, of course, then the question is, okay, well, if you release the sensor data for all of these, how are people even going to download it? And so then we did some very interesting things. We released vectorized data of the environment produced by our sensors, by actually novel systems. We have a system called auto-labeling, which I think is pretty key for the autonomous driving space, which in hindsight, after you observe the whole scene, you can try to, as perfectly as possible, recreate everything that happened, right? And we have novel work on this. It's published maybe a year ago or 2 years ago. And with this work, we actually made our data set. And it's still probably state of the art of what you can do with these models. It's very clean data of a kind that was never done. And so you can study aspects you could not before.
And have people engaged with it in ways that were unexpected? Has it been useful to you?
People come up with very powerful models, which is part of the appeal. And you have people from industry, from academia, even kids from high school in some cases, like 1 hour challenges, which is really impressive to see. Just the broad, it's worldwide reach. What's interesting is, like, we release it with some problems in mind, and we help try to suggest problems. And the way we try to suggest problems is we've been running challenges for 3 years straight with prizes. And so we say, here's a problem, here's a metric we believe is suitable for this problem, right? Like, please submit. Here's the leaderboard. Here you can submit. If you do well, you can win, and come to our workshop. This year we also have a workshop at CVPR, one of the two premier computer vision conferences. You get to present, right? And people participate, and every year we expand the set of challenges that we have. So this year we have 3 completely new challenges. Some are really unique that have not been run. So occupancy prediction, future occupancy prediction, both for occluded and unoccluded agents with flow. There's few such challenges. We have one on actually from 5 cameras over time, can you reconstruct the 3D boxes accurately? Like, there is variants of this for a single camera, but for multiple cameras over time with rolling shutter, which is a real setup on the car, we worked out some very interesting metrics and setup that has not been done before. That is very core. Like, I think that, a lot of people do appreciate, I think, the releases, and I think the more we release, the more different research people can do, because now they can study how all of these enrich each other and how the perception and motion data set, they have certain compatibility. You can reason how to combine some of these, and it gives you a lot of opportunity. But the last point is, people started solving problems we haven't thought of with this data or do different research, including ourselves. So, for example, you can use our data to, say, train nerve models. We have all this rich data from all over the place. You could do that, or you can train 3D reconstruction models, right? You can do shape completion models. There's a lot of things you can do when you have such rich data with these 3D. When we release 2 sensors, camera and lidar. If you have camera and lidar in interesting environments, you can do a ton.
Cool. Is it a challenge to convince the business that it's a useful thing to release this stuff? Is there objections that, like, there's IP that might kind of leak out, or even like privacy issues possible?
There were objections. I think ultimately people, I'm thankful, and Waymo is a great place to have a research team. I think it's a great collaborative environment with people that really appreciate the value it can bring, especially in an open-ended field. I think you can really balance the concerns, right? I don't think with us releasing the open data set, it will give such a huge leg to the competition, because we released some data for people to study, problems in this space, right? I think ultimately it's really helpful to everyone, but it's not defining. I think there's a lot more positives for everybody than worries for Waymo. And by releasing it, we hopefully struck a good balance. And it has been a lot of work. Ultimately, we want to release data and at a quality that befits the Waymo brand. That means that we need to take, say, blurring all the faces license plates well. We need to make sure that the annotations are very high quality, which they are, right? We really paid a lot of attention, and we ran models to keep mining for potential errors in our 2D and 3D annotations. I think they are very high quality. And so hopefully people can benefit from that.
Well, look, we always end with 2 open-ended questions that I'd love to try before you go. So one is, what do you think is kind of an understudied part of machine learning, or something that you would want to look into if you had more time?
Well, I would say that I'm perfectly happy doing the problems we have, because ultimately they cover most machine learning problems are represented in our domain. I would say a few. So one of the fascinating areas that we're looking at is, and AVs really stresses, you want robust systems, right? And we touched on this. So what does that mean, right? And this means many things, and it depends which system. So one of them is you want to build inductive bias and structure in the, if you think of the whole thing as one big architecture, you want to build the right structure so it generalizes, right? This means picks the right API, pick the right designs and representations. There is a certain flow in our models, which I think now became a lot more popular in the whole ML community. Like you go from perspective view with tens of millions of points, scans, you name it, right? And then you create a Euclidean space, maybe in top-down view, with ultimately, how would I say, with objects, with relations, with polylines or structure. And in that one, models generalize a lot better. So you want to do more of this. That's one. The other one, which we touched on very briefly, but a big part of it is when you train these systems and make them robust, you need to be able to detect the rare examples, right? So why do you want to detect in rare? I mean, if you detect the rare examples, you can, of course, bias your training set and metrics to make sure you do well on them, right? When you drive, like if you know you don't know, it's already a huge help because like machine learning models, you can think of them, they're very performant when you trust them. And if you don't trust them, you can fall to something a lot like more cautious and safe. You just need to know when. And so there's a lot of techniques you can study to do this. And we can talk about finding rare examples if we get to it. But we have a whole bunch of research on this. We can maybe after let me. There's another one that I find fascinating, and we touched on. This is domain gap between simulation and real world. How and what should be the simulation such that you can train the best possible autonomous vehicle stack? How do I build it from the data I collected? What are the metrics for the simulator that it should optimize as realism? And then how do you put planning agents in it, right? I think that is a fascinating.
Can you give me some examples of results in that? I'm not familiar with that work.
I mean, so there are several things you can do. There are several aspects of realism. So you can think of it when you put your vehicle in the simulator, you want to produce inputs to the vehicle that are similar or highly similar to what you see in the real world, right? Then the outcomes in the simulator are pertinent. What are the inputs to your, vehicle, right? It's sensor data, and it's the behavior of other agents in the simulator. So these are the two main axes, is some kind of sensor data, perception realism. Maybe you do some intermediate representation that's a lot cheaper than simulating every pixel, but you need something. And now you need agents to behave realistically, meaning they react to you. Agents need to react to you, right? Like you do something different, this simulator needs to like cause and effect. It needs to, there's a reaction. It needs to be reasonable, right? Now, how reasonable does it need to be? Well, it varies. Even so, as you know, like there is a strong work on domain randomization in other domains. If you want to train a more robust model, you can even try somewhat unreasonable things. As long as there's enough of them, you can build a more robust model. In our domain, you also want simulator to ideally be a good measure of risk. And that's a higher requirement. Then you need taller level for what realistic means, because it needs to be somehow correlated to the real rates.
Mm-hmm. But how would you even know that though? If it's reacting to what the agent does, how do you quantify how good your simulation is? Like the agent might do something that you never saw in the real world. How could you even know if the simulation is realistic?
So there's two measures in which you can measure realism of agents that we think, and we've presented in past talks. Is one of them is, Turing test of sorts. You look at the scene. It's like, could this agent have done this? Is it likely or completely impossible? That's one. So that's a proof of existence that it's realistic. Then you have distributional realism, right? Which is, say, how often someone will cut off in front of you, or what is the braking profile, or how long does someone take to pay attention to you, right? That is the type of useful distributional realism that you can enforce. And this makes sure that agents behave at least on a distributional level similar to what you observed. Now we observed a ton of behavior, right? So we have enough data to know roughly what the distribution of these things is. That one of the challenges is, I mean, agents acting in a continuous space, it's somehow practically an infinite distribution. But you can take slices of it that are meaningful and enforce that those are matching. Right? So there's certain design there that you need to build in.
I would imagine there's like parts of the distribution that you might care about, but it would be dangerous to even do in the real world, but you might really care. Like what happens if you slam on the brakes or, make like a hard turn? Like
you can play any future you want, right? In theory, if you build it right. I think that simulator has this like huge scaling promise. You take any scenario you saw, and you release the agents, and you release yourself, and you can try all kinds of stuff, and they can try all kinds of stuff, and you can learn from that, right? So it multiplies your data via, if you have good models for the agents, now you have 100x multiplier on everything, right? And that's fascinating. And maybe if you can score roughly how likely each future is, then you have even a likelihood estimate, right? You can sample adversarially and bias yourself towards the interesting cases. Try someone to try to cut in front of you when you're riding. Most of the times they don't, and maybe 1% they will. Then you see what happens if they try. There's different ways to build it, but you have opportunity, if you do it right, to really dramatically increase, say, the cases of collisions you can replay. Because we don't see that many collisions, thank God, right? Even when we drive a lot. But I can make you a lot in the simulator. And some will be more realistic than others, and it makes you a nice area to study these things safely, of course. It's the best if that's where you study them, right?
Right. Do you have more thoughts on finding unusual examples? I mean, active learning has been around for a long time. It's like something that I think most companies use when they want to actually deploy something, to production. Are you kind of talking about active learning or something kind of more complicated here?
So I will say a few things. Some of them are papers of ours, observations. Ultimately, right, our domain is ripe for finding the rare examples. It's one of the main tasks you need to do, right? I mean, most of the time you drive, it should be boring, right? And you need to find, and we collect a ton of data, which is great. So almost the setting is you have some proxy for infinite unlabeled data. And you have some labeling budget, of course. You can label yourself some data. As you know, you run a labeling company. Now, how do you benefit the most from this data you just collect, right? And so most of the examples are somewhere if you can find them. So that's the first observation, right? And so that's one. Now, if you were to find them, you can data augment a lot out of them. That's a good way to go, right? And we have papers on how to perturb them in different ways. You can do this for cameras. You can do it for LiDAR. You can even machine learn how to best perturb them to get best results. We've done work, right? I think I'll get to you in a second about ways to find rare examples. So there is a long tail learning literature typically. And a lot of the long tail literature was done, driven in academia by data sets such as ImageNet or some I don't know, is it BIRDS data set? There is one. We used to do it.
Small data set, yeah.
We used to do at Google when I worked for Google Goggles, like breeds of dogs and,
right.
types of birds and types of food and all kinds of things, right? So typically the literature in long tail is driven by these rich semantic data sets that you have some very rare thing, I don't know, like a rare breed of bird or a rare breed of plant, and then you need to detect it with 5 examples, right? But that is a world in which everything was named. And so just this name was rare, and you just had 5 examples. So let's maybe learn to do the most with them. That's one way. Now, in our world, it's a little different. So in autonomous driving, you don't want to name every type of plant or even every type of dog, right? So you have fairly broad category. Take the category vehicle. To an extreme, right? There's all kinds of vehicles in the category vehicle. And 80% of it will be like boring sedans, say. And then down the line, you can have all kinds of strange configurations of things people do, right? Cement mixer with a trailer or something, or trams on the road. I mean, you can have. So now in this big bucket, like what is a rare example? You don't want to name it. And rare is not the same as hard. That's also this property. So I'll give you an intuition. And I think the people sometimes say, oh, we're gonna train an ensemble, and where the ensemble disagrees, we'll just label, right? That's very standard. Now, what's the problem there? Well, the ensemble finds hard examples. Models disagree. Not easy to tell what it is. That doesn't mean it's actually, first of all, rare, second, beneficial to label. And you can see this intuition maybe the easiest in lidar perception. So you do lidar perception. If you do ensemble mining, we've studied this, actually a great guy in memory research called Max studied this, you get cars in parking lots far away. They have 5 lidar points. The models clearly disagree how the bounding box should be, but that's not a very useful example. Like, it's not like if you mine more examples with 5 lidar points, you'll get much better on them, right?
Right.
And so you need some mechanism to tell rare from hard.
So what do you do? What's the intuition?
Well, you can build, for example, a model that estimates given features of the examples, a distribution, and check which are actually rare things versus one you've seen a lot, right? And we have paper on this still unpublished, so I will not say more, but it hopefully will be soon. Obviously, that's one way to think about it, but I just thought it's an interesting distinction. There's another work we did, which is called Gradtail, that is published. And that's a bit of the same idea. It's like, let's define long tail as kind of uncertainty related to the model or the task you're doing. It's not so much that some class is long tail somewhere, right? So it's epistemic uncertainty related to the model you're training. And what does that mean, really? And again, this comes to say, actually, Zhao Chen, who is the author of that, primary author of that paper, has this reasoning. Well, some rare kind of apple is really important and relevant when you try to tell the types of apples. But if you try to tell apples versus oranges, that's maybe not even the relevant case, right?
Right.
And so we have a definition of long tail, which is if an example, when you train it, has a gradient that is orthogonal or different from the mean gradient for the class.
Sorry, how do you define a gradient for a label?
I mean, you backprop you can backprop the gradient for an example through some layer, and you can check on average what examples from that class have as a gradient around this time. And if you have different gradient, and actually you can be either orthogonal or negative. So you can argue which one is which, but like if you have different enough gradient, it's ultimately long tail example. And sometimes you find different examples that semantics does not give you. For example, these types of examples have maybe a class fridge, but the fridge is open, it has some strange point of view. That's a rare example. The class is common, right? You can predict depth or regress something. The rare example can be the depths of points far away that are close to something occluded. Like, you can't even name these things, but that doesn't mean that they don't exist. The long tail and semantics are different concepts. And so we've explored this a bit because it's relevant to our domain.
Is the intuition that these change your model the most?
I mean, the rare examples, they will improve the model the most because you can actually learn it.
Right.
If you feed it. As opposed to the hard one, I mean, you can feed it, but model will waste capacity trying to solve something that's hard to solve in the first place. So, but when mining, it matters. Now, of course, there is a whole meta point, which is, what is an example you should mine? Like, if you have a full-on integrated eval of the whole system, you can try to introspect in the system, and at that point, the example you should mine is the one that caused you troubles downstream. Right? So that's the optimal world in which you mine. The problem is that now is complicated because it couples all your system and evaluation. Right? So if your evaluation is perfect, you should do it. If not, then some of these simpler, more modular approaches give you a lot of the benefit with a lot simpler set.
Cool. All right. Well, I want to make sure I get my last question in, which is basically what's the hardest part of making this stuff work in production? Like when you think about, like from just like soup to nuts, making autonomous vehicles work. What's the step that's like most unexpectedly challenging?
So which question is this? Is this from research to production? What's hard, or what is hard about
Research to
AVs?
production, exactly. So like you have something working in research or something like working in like the open dataset challenge or like a thing that works in a Kaggle competition. And now you need to like make the car go. Where does this break down the most?
I mean, I'll tell you. Actually, my first experience with this is I was at Street View, and that was maybe 2007, and I learned how to say automatically calibrate the camera on the car to the IMU and the GPS system. Every once in a while, they were miscalibrated. The panoramas were all crooked in strange ways, right? And you don't want to do it manually because there's so much data. So I came up with a system that did it, and I had great results maybe in 2 months, say. And then it's like, all right, let's ship it, right? And then you start, like, I run it now on a lot more results, and I see all kinds of issues, right? And someone put a bag over this thing. In other cases, the car got stopped for too long, so you can't do like structure for motion. Like you just find a bunch of them, and that was maybe 3 more months. And then you run it, it's like, oh, I'm there. And then you run it again, and of course, in a large enough data set, everything that can go wrong does go wrong. And then you find a whole set of yet more rare cases that you need to worry about. So 3 more months on those, right? Like, and I think that to me taught me, oh, I see. So from something that works good enough on a demo case, which is typically a paper, to
Right.
something actually working, there is still a big chasm. And I think a lot of it comes from additional requirements. So for a paper, you have academic metrics. They're usually permissive. They're usually fairly average type metrics over something, right? And you have, the only constraint is, okay, there's this 1 or 2 metrics you picked, and let's show the main ones, and let's show it works well. And then you go to the production folks, and they say, oh, but we want this model to produce 3 more things, and this rare case that it doesn't work on that it should work on. And, furthermore, it needs to run like 3 times faster, right? And you need to build it into this system with these constraints. And you're like, oh, great, right? Like now my work maybe tripled or quintupled. And then all the downstream models have to work with it too. It can't break them now. It maybe produces new signals. Now I need to work to fix those, right? And so that's the usual, I think, story of how to get a research model in production is, you need to persist and go. There's a stage 2 or 3. Now the issue there is, like even if 1 or 2 people are enough to get the demo result, they may not be enough to push the thing to the production. So now I need to, ideally, and we're lucky that we have a lot of great collaborations with the production teams, so you just do it together, right? And then it's several people, and you need a lot more people ultimately to do this, right? And that's why also in research, like we are applied research team. We are not there to try every possible thing and learn something. We're trying to ideally guess the right things to try, show that they work, and then spend sizable effort if needed to build infrastructure integration. Often like frameworks even, jointly with the teams, such that many people now can accomplish it successfully. So that's why the team is not too small either. Like when you actually have applied aspiration and shipping aspiration, you usually need larger teams. So now you need fewer larger efforts, because that's what's conducive to actually landing the things beyond papers.
Right. Awesome. Well, thanks so much, Drago. This is really fun.
Great talking to you. Yeah. Likewise. Thanks for having me.
If you're enjoying these interviews and you want to learn more, please click on the link to the show notes in the description, where you can find links to all the papers that are mentioned, supplemental material, and a transcription that we work really hard to produce. So check it out.